In this video, we're going to consider the global picture of our square plate broken into small square subunits with different temperatures in the environment along each edge. What we do know is that we expect around this edge to be hot because we have a temperature of 120 in the environment there. Medium hot along this side, it's almost as hot but not quite. And we certainly expect to see a cold edge along the vertical side. Along the insulated wall, we don't get any heat, so we expect to see a gradation from medium hot down to cold here. And what happens in the middle, we don't know. This is all part of what we're aiming to compute, is what are the actual temperatures quantitatively in each of these cells once we reach steady state. Well, let's start by looking at one cell to begin. We're going to look at T12. We're going to assume that it's the coldest one out of all its neighbors. Is that a problem? No, because if that's not true, we're just going to get a reverse in the heat flow. What we're going to work with as our starting point, very similar to trusses we've seen earlier, is that the sum of the heat flows into the cell is going to be 0. Why would we say that? Because we're looking at a steady state model here. What does this temperature stabilize down to after a few minutes or seconds once we've put this environment around it? Well, we also know how to calculate all of these Q's. These Q's are built out of the differential equation model, which ended up being negative K A over delta X times delta T. And the delta T could be T12 minus T13. There's some heat flow between those two neighbors, plus the same thing times T12 minus T7. Same thing, T12 minus T11. Start to see a pattern here. And then the negative Ka, T12, and what's missing is T13. Delta X, T12 minus T13. All of that sums to 0 at the steady state. The nice thing about using convection all the way through is that all of these constants go away if we have this all equal to 0, and then we can start grouping terms. It's an arbitrary choice here, but I'm going to keep the negative sign, so we end up with negative T12. And notice we also have another negative T12 here, another one here, and another one here. All in all, that ends up being negative 4 T12s. What are the other elements? Well, let's put them in numeric order this time. We have 7, T7, we'll have T11, we'll have T13, and we will have T17. Those have to add up to 0 as well. That's an interesting mix. If we take a look at that, that makes a nice linear equation with the T's unknown, and this will be perfect for putting it in matrix form. Just for a sense of interpretation though, I'm going to regroup this and solve for the T12 part. T7 plus T11 plus T13 plus T17. If I bring this over to the other side, it becomes positive. And divide by 4. And lo and behold, what this model of steady state predicts is that if we break our square region here into small cells, then when we have neighbors, this one will equal, its temperature will equal the average of the neighbors' temperatures. And that seems entirely reasonable at steady state. We have some hotter, we have some colder. To be in equilibrium, this cell here would have to be the average of the temperatures of the cells around it. So this is a nice conceptual place to start. This is going to turn out to be the form of the equation that's easier to work with in MATLAB, but there's a nice simple relationship. One is just this equation rewritten more as a straight line, everything equals 0 form. So that's T12. We can see exactly the same logic would apply to T13, T7. In fact, all of these interior cells here. Where things might get a little different is along the border, either of the insulated wall or of the environment. Let's take a look at those cases next. If we look at T1, there's two artifacts here. There's an insulated wall that we would say there's no heat transfer going through that at all. However, there are 3 other contact cells, 2 of which are neighbors, and 1 of which is the outside environment. Based on the inspiration we saw before, what we can do is look at the T2 and say that the heat flow, again, we're going to say sum of heat flow equals 0, but we'll take out those common coefficients that show up in the heat flow equation, and we'll find the difference between T2 and T1. We'll take the difference between T6 and T1, and we'll take the difference between 20 and T1, add that equal to 0, and all of this would be times Ka over delta x times this whole thing. But that would just cancel away because the right-hand side is 0. We would just be left with these unknowns. So let's take a look at the pattern we get from that. We have negative 3 T1s, and we have a T2, and we have a T6, again the neighbors, and there's also this 20 that I'm going to move to the other side for a second, because this is going to help us build the matrix form again. That's where we're headed. But this looks very similar to the earlier equation, where we have a sum of temperatures with the cell that we're looking at having a negative coefficient, and this time we have an external temperature. Well, that's something that we can move to the right-hand side. There's also another important ingredient here. This 3 is essentially the number of neighbors with heat transfer. For this particular cell, we do not have any heat transfer through the insulated wall, so we only have 1, 2, and 3 neighbors. That's why we have a negative 3 for this particular cell, balancing the heat in and out of cell 1. Let's take a look at one other border situation, one other border case, T5. This time we will definitely be transferring heat in 4 directions. If we add up the Q's equaling 0, just have to make sure that we keep the 120 and the 20. So we already know that this temperature is going to be somewhere between 20 and 120. If we factor in the other ingredients, though, we'd have the same kind of form. Let's take the T4 minus T5. The heat flow from 7, 8, 9. This will be T10. We'll have T10 minus T5. Then we'll have the 20 minus T5 and the 120 minus T5 equals 0. If we wanted, we could put the Ka all over delta x times all of this. That's what would give us the heat flows, but again, those cancel. And so what we end up with is negative 4 T5s plus the 2 neighbors, each with coefficient 1, and taking the 20 here, bringing it over, minus 20, take the 120 over, minus 120. That is our steady state condition for cell 5, for T5. What this shows us is that through a process very similar to the truss analysis, looking at each joint there, here we're looking at each cell, we can come up with a linear equation for the temperature balance of this and its neighbors. And by the time we're done, we will get 25 different equations out of this process. Having now constructed all of these equations, we can imagine what that would look like if we took them into a matrix form. Particularly, if we built a column of unknown temperatures, T1, T2, T3, all the way down to T25, and we built our B vector here, that would be B, that would be T, we could see then our big matrix here that we would call A. If we look at the balance for T1 and label that in an equation here, we would get a coefficient of negative 3 T1s. Well, that's just a negative 3 times T1. We'd have a 1 in the second column for T2. And then, let's put a little vector on here. Then we'd have a gap. We'd have some zeros. 1, 2, 3, 4, 5. And then T6 would have a 1. And that would be it, because we would move this 20 to the other side, and it would become a negative 20 in the B vector. Everything else in that row would be zeros. Further down, if we were doing T5, we would have some entries in between, but T5, we would scan across and say there's no T1s, no T2s, no T3s. There is a T4, There's minus 4 T5s. There's a T9, so we go on for a while. 5, 6, 7, 8, 9, have a 1. Then we'd have these values here brought to the other side as negative 20 and negative 120, or negative 140, to match that same row. Again, if we took the walking fingers here and multiplied this row by these t's, we would get this part of the equation, and then we just put any constants from the outside appearing on the right hand in the matrix form. Now we could do the same thing for T12. What we'd start to see then, if we look carefully, is a really nice structure. We'd see some elements down the diagonal, because if we're looking at T1, we end up with a negative big number in front of T1. If we looked at T2, we'd see the same thing in front of T2, and so on. We'd also see 1s in the columns corresponding to the neighbors of each cell. So if T1 is what we're looking at, we'd see a 1 in T2 and T6. For T2, we'd see the neighbors T1, T3, and T7. For T3, we'd see the neighbors T2, T4, and T8. So there'd be some really, really nice structure in this matrix.